Alright, so for drawing representations, we are referring to Lewis structures, and we have a little box at the top that's summarizing how electrons reach the octet rule for both types of these ions. Sorry, not ions, both of these bonding. So ionic bonding has a metal and non-metal ion, and they transfer electrons, and we draw that using arrows to show where the electrons are moving from the metal to the non-metal. For covalent, we're going to share using share pairs between nonmetals, and sometimes we might have to have a double bond, and then we put lone pairs around, but we always need to make sure that every element has a complete octet, and that we only use the amount of valence electrons available. So when we're drawing these, if it says electron transfer, then this is referring to ionic. And if it says sharing, then this is referring to covalent. And you'll just draw them as such. So our transfer, we've got beryllium and phosphorus. So beryllium, each beryllium has 2 electrons. And each phosphorus has 5. So we have 3 open spots around our phosphorus. And we'll start transferring. And remember, we add elements to fill those until all of our spots have been filled appropriately. And now we have filled all the spots. So we've got 3 beryllium and 2 phosphorus. There's our chemical formula and the electron transfer that takes place between them. Now for electron sharing, we have carbon tetrachloride, that's CCl4. So we need to count our valence electrons. Each carbon is going to have 4. Each chlorine has 7. So if we add those up, we got 4 of these. It's going to be 28 and 4, 32. So there's our electron, valence electron count. So this is just kind of a workspace here, counting our valence electrons. Now let's actually draw it. So put our carbon in the middle, shared pairs with chlorines all around, and then we're just going to surround by lone pairs to complete each octet. And now let's go back and count and see if we used our 32. I'm going to count by 2s. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Hurrah! So there's our electron sharing for carbon tetrachloride. And this is a tetrahedral shape. It would be a nonpolar compound, and its intermolecular forces, you would have just LDF. So if we were to finish that out for covalent structure and all the stuff that we know from it. So as you go through the rest of these, you're just following, if it's an electron sharing, you're going to draw it like covalent. You're sharing between them and then adding lone pairs. We have another electron transfer, and then sharing. And don't forget, when we have a negative charge here in our polyatomic ion, those are extra electrons when you're doing your count. So if we were to count our valence electrons, kind of like we did in the previous problem, there's 3 of these. So we have 4, and then we have 6, 3 times it's 18. And then we have the extra 2 electrons from that negative 2 charge. So our total count here is 24. That's how many, this is just our work area. Okay, so 24 is what we need to have in our sharing when you draw your Lewis structure. Let's go ahead and finish this one off. So we'll put 2 dots to finish that octet, and then we'll add lone pairs here. And now let's count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Wah, wah. Now we need to double up. So I'm going to take 2 of these individual pairs and share them. And now we have 24. This would be my electron sharing. Remember, when we have a charge for a polyatomic ion, we just put it in brackets with the charge in the upper right hand corner. A little note that we never talked about, but you might hear it in further chemistry courses if you take them, is called resonance. And so this double bond essentially could be between any of the carbon and oxygen bonds here. So resonance just means showing all of the possible structures of where that double bond could be. So it's just kind of repeating the same drawing, but showing all the different spots where that double bond could be. It could be on the left, it could be on the right, it could be on the bottom. And that is called resonance. We're not going to test on resonance, but I just wanted you to be aware of that concept. If you ever hear someone ask you for resonance structures, that means show me all the possible ways that you could draw this for where the double bond could be. And because that double bond could be in any of these positions, sometimes you'll also see it drawn like all of them having a partial double bond, kind of like this. If you ever see it written like this, that's why. But it's a little bit more confusing and harder to see where all the electrons are at. So I prefer, and most chemists agree, to draw them individually, not with the like half bond between them. But that's resonance structures if you ever come across that. And you can finish the rest of these. Good luck!